To understand how the first stars and galaxies formed, astrophysicists must calculate the Lyman alpha escape fraction. Lyman alpha is a specific spectral line of hydrogen in the ultraviolet, created when an electron drops from its second lowest energy level to its lowest. Predicting this fraction is difficult because Lyman alpha photons are resonant, meaning they are frequently absorbed and re-emitted by hydrogen gas. This causes them to scatter chaotically through the clumpy interstellar medium rather than traveling in a straight line. The current standard for modeling this behavior uses 3D Monte Carlo radiative transfer simulations. These models use repeated random sampling to track millions of individual photon scatterings, a process that can require weeks of continuous supercomputer time per galaxy. The thermal angular symmetry law, or TASL, proposes an alternative framework that targets these same escape fractions without relying on stochastic sampling. TASL treats photon escape as a deterministic problem governed by spectral geometry. Under this model, the physics that usually requires weeks of simulation is resolved through a calculation that takes minutes. Moving from weeks of computation to minutes for a single galaxy increases the processing speed by a factor of 10,000, allowing for the analysis of datasets that are currently limited by a simulation backlog. Astronomers identify these processes by observing three specific hydrogen emission lines: Lyman alpha, H alpha, and H beta. H alpha and H beta are visible Balmer lines, created when electrons drop to the second energy level from the third and fourth levels, respectively. Traditional analysis treats these three lines as independent signals to be measured and isolated from one another. The TASL framework instead views these lines as components of a single unified resonance system. This system functions like a physical spring. When Lyman alpha photons are trapped within a galaxy, the spring is in a relaxed state, and the galaxy's spectral energy is dominated by the redder H alpha and H beta lines. As the physical conditions within the galaxy shift to allow more Lyman alpha photons to escape, the spectral spring compresses. This energy balance shifts toward the ultraviolet. This chart shows the energy-weighted effective wavelength of the spectrum. As the Lyman alpha peak grows, the indicator tracks the systematic blueward shift toward shorter, higher energy wavelengths. This shift provides a measurable proxy for the underlying geometric state of the system. To quantify the state of the spectral spring, we must define the formal axioms that govern the energy distribution between these lines. This chart shows the energy partitions of the system. According to the axiom of energy partition conservation, the fractional luminosities of the three lines must sum to exactly 1. We then assign each line an angler, denoted as theta. This physical angular magnitude represents the intrinsic spectral geometry of the specific line. For this hydrogen system, the anglers are fixed. Lyman alpha is approximately 36.4, H alpha is 196.7, and H beta is 145.7. There is a significant mathematical gap between these values. The angler for Lyman alpha is notably smaller than the values for the Balmer lines. Because the anglers are constants, any change in the system's geometric state is driven entirely by how the energy partition fractions shift between the lines. We find the overall geometric state by calculating the effective angler, which is the energy-weighted average of the three individual line values.
When the Lyman alpha escape fraction increases, the Lyman alpha partition fraction grows and begins to dominate the total energy budget. Because Lyman alpha has the smallest angler value at 36.4, its increasing dominance means the total effective angler is mathematically dragged lower. This leads to the axiom of spectral angular duality, which states the effective spectral temperature is inversely proportional to the effective angler. By dividing the universal TASL constant of roughly 6.22 million by a shrinking effective angler, the effective spectral temperature is guaranteed to rise. A higher escape fraction is mathematically locked to a higher spectral temperature. This approach appears to ignore the microphysics of clumpy dust and gas turbulence that traditional simulations spend weeks calculating. However, this method follows the established logic of classical thermodynamics. To determine the temperature and pressure of a room, physicists do not calculate the exact trajectory of every individual gas molecule. TASC treats the galaxy's radiative system in the same way, viewing the complex photon scatterings as an ensemble. The local complexities average out, allowing the effective angular and temperature to act as macroscopic state variables that bypass the need to track individual photon paths. To validate this model, we must test its predictions against empirical data from observed galaxies. We applied the protocol to a sample of 5 star-forming galaxies from the LARS sample, which have independently published escape fractions derived from traditional simulations. Comparing our results to published values, TASC predicted HARO 11's exact escape fraction of 3.0% and its lowest effective spectral temperature, the relaxed baseline of our spectral spring. Across the entire sample, the average deviation from supercomputer models was just 4 percentage points. The fact that this mathematical sequence tracks perfectly across varied galactic environments confirms the physical basis of the spectral compression ladder. The most precise demonstration of the framework's physical grounding is actually found in the high-escape galaxy LARS 2. For LARS 2, the TASL formula predicted a 52.1% escape fraction, an exact match to the published dust-corrected value with a deviation of less than 0.1%. The dataset did include an apparent deviation in LARS 1, where the TASL framework overpredicted the escape fraction by 9 percentage points. This overprediction occurred because the TASL method uses raw, dust-attenuated observational fluxes, while the published literature value used a dust-corrected figure. This discrepancy indicates the framework implicitly accounts for dust as part of the system's geometry, validating the use of direct observational data without secondary modeling. By condensing a months-long modeling effort into a calculation that takes minutes, this framework provides a deterministic tool for rapid analysis. Researchers can now perform statistical studies on decades of archival Hubble Space Telescope data that were previously too computationally expensive to process at scale. This utility is immediately applicable to the flood of data regarding galaxies in the epoch of reionization, the period when the first stars and galaxies cleared the fog of neutral hydrogen gas that filled the early universe. TASL offers a path to unblock the data pipeline, providing astronomers with a way to calculate how the first galaxies illuminated the universe.